For more than half a century, airlines and engineers have been locked in a race to build bigger, faster, and more comfortable passenger jets. From the sleek elegance of Concorde to the double-decked Airbus A380, these machines were built to change the way the world travels. But how do you even build something the size of a skyscraper and send it safely into the sky? Today, we're going inside the workshop to see exactly how the 10 largest passenger jets in history were made. We'll follow them in historical order, not size, to see how each generation pushed the limits further. The Boeing 707 was the plane that replaced propeller planes and made long-distance travel much faster and easier. At 46 meters long with a 44-meter wingspan, it carried about 180 passengers in early layouts. Its fuselage was built from conventional aluminum alloys, joined by riveting techniques honed during World War II bomber production. The wings were reinforced with steel spars, while titanium was used sparingly in high-stress fittings. The JT3D turbofan engines were podded under the wings, which reduced cabin noise compared to earlier turbojets. Engineers developed modular wiring looms and hydraulic systems that could be rapidly installed. Inside, engineers designed a circular fuselage cross-section, strong enough to hold pressure at high altitude to give passengers a quieter ride compared to propeller aircrafts. Air conditioning packs and sound insulation were integrated beneath the floor, which made long intercontinental flights more comfortable. At 62 meters long with a 25-meter wingspan, Concorde carried only about 100 passengers, but at twice the speed of sound. Built from aluminum alloys capable of withstanding 127 degrees Celsius skin temperatures at Mach 2, the fuselage expanded several inches in flight. Engineers designed sliding joints and flexible wiring harnesses that could stretch with the airframe. Titanium was used in heat-critical areas such as the engine nacelles. The delta wings were built in sections and joined with precision drilling to optimize both supersonic cruise and subsonic stability. Concorde's fuel system was one of its most unique engineering feats. Pumps shifted fuel between tanks mid-flight to balance the aircraft's center of gravity as it accelerated through the sound barrier. For passengers, Concorde meant a 3-hour flight across the Atlantic in unmatched luxury, though cabin size was sacrificed for aerodynamic efficiency. The L-1011 TriStar was one of the most technologically advanced jets of its era. It measured 54 meters long with a 50-meter wingspan and seated about 270 passengers. Its fuselage was made from precision-machined aluminum lithium alloys, with titanium used in the landing gear and engine pylons. One of the most innovative features was its autopilot and auto-land systems, which were integrated during assembly with redundant wiring looms and hydraulic circuits. Engineers also optimized the wing with advanced high-lift devices which were installed using laser-aligned jigs for accuracy. The Rolls-Royce RB211 engines required composite fan blades. Though costly, they gave the aircraft quieter performance compared to rivals. Passengers enjoyed smoother and quieter rides, which gave it a reputation for comfort that outlived the jet itself. The DC-10 was another tri-jet that measured 55 meters in length with a 50-meter wingspan and seated around 270 to 300 passengers. The fuselage was built primarily from conventional aluminum alloys, but engineers reinforced the lower lobe with titanium fittings to handle the stress of its unique third engine mounted in the tail. Riveting dominated assembly with tens of thousands of fasteners joining the large fuselage barrels. Modular wiring harnesses and pre-installed hydraulic lines sped up production. The later MD-11 introduced composite materials in control surfaces and winglets to improve efficiency. Extended range versions required redesigned fuel systems with pumps capable of handling higher flow rates across multiple tanks. For passengers, the DC-10 and MD-11 offered wide cabins and long-haul capability, setting a standard for international travel in the late 20th century. Russia's answer to the wide-body race, the Il-96 combined traditional metal construction with selective use of composites. The fuselage was built from high-strength aluminum alloys with carbon fiber panels and control surfaces to save weight. Titanium was widely used in landing gear and engine pylons. Its sections were built in Voronezh and joined using hydraulic jigs and robotic riveters. The jet measured 65 meters long with a 60-meter wingspan and carried up to 300 passengers. Il-96's 4PS90A turbofans engines were equipped with wide-chord fan blades, giving it quieter performance than earlier Soviet aircraft. Engineers also installed advanced avionics and redundant fly-by-wire controls for improved safety. Passengers experienced a quieter, more comfortable ride compared to its predecessors, though the Il-96 never achieved widespread adoption outside Russia. The A340-600 was one of the longest passenger jets ever at nearly 76 meters. It had a wingspan of 63 meters and could carry up to 380 passengers. The fuselage was built from high-strength aluminum alloys reinforced with titanium in the wing roots. Engineers designed the wings with composite spoilers and winglets to reduce drag. Assembly involved modular fuselage sections built in different European plants, then transported by Beluga aircraft for final joining in Toulouse. The four Rolls-Royce Trent 500 engines were mounted on pylons, designed with titanium fittings to absorb vibration and thrust loads. The long fuselage required additional fuel tanks and a reinforced floor structure to handle passenger and cargo weight. Inside, airlines could configure luxurious layouts with spacious cabins. For travelers, the A340-600 offered long, non-stop flights without refueling, though at the cost of higher fuel burn compared to later twin jets. The A350-1000 represents the cutting edge of composite passenger aircraft design. Nearly 53% of its structure is carbon fiber reinforced polymer, including the entire fuselage and wing panels. This dramatically reduced weight compared to traditional aluminum. The wings were designed with a unique curve that automatically adapts in flight, improving lift and reducing fuel burn. Each was assembled using automated fiber placement machines that laid down precise strips of composite tape before curing them in massive autoclaves. Titanium was used in landing gear and engine pylons to handle high-stress loads. The Rolls-Royce Trent XWB engines were integrated with nacelles designed for laminar airflow to reduce drag and noise. Passengers experienced quieter cabins, larger panoramic windows, and LED mood lighting. Airbus also installed advanced air filtration and higher cabin humidity levels to reduce fatigue on long flights. The A350-1000 demonstrates how material science and production automation can directly shape both efficiency and comfort. The Boeing 777-300ER is among the largest twin-engine passenger aircraft ever produced. It has a length of 74 meters, wingspan of 65 meters, and could carry 396 passengers. Building such a giant with just two engines demanded radical material and design choices. The fuselage is built from advanced aluminum-lithium alloys that combine lightweight with fatigue resistance. The 777X goes further by using the largest composite wings ever built for a passenger jet. These wings were cured in giant autoclaves and feature folding wingtips, so the jet can fit into standard airport gates. Assembly lines were reorganized around modular sections. Pre-wired panels and pre-installed hydraulic systems were snapped into place to reduce production errors and speed up final assembly. The GE90 and GE9X engines, the most powerful turbofans in history, were built with ceramic matrix composites capable of withstanding higher temperatures, boosting efficiency. For passengers, the benefits were clear: longer non-stop routes, larger windows, higher humidity levels in the cabin, thanks to improved fuselage sealing and lower cabin altitude. These engineering choices made ultra-long-haul flights more comfortable than ever. The Queen of the Skies was stretched to new limits in the 747-8, the longest passenger aircraft ever built at 76 meters. Production took place at Boeing's Everett facility, the largest building in the world by volume. Fuselage sections were built from high-strength aluminum alloys and riveted together using robotic systems capable of drilling and fastening with millimeter precision. Engineers redesigned the wings with raked tips and integrated composite panels that cut drag and improved fuel efficiency. The engines, GEnx2B67, adapted from the 787, featured composite fan blades and titanium leading edges. Not only did they improve range, but their quieter operation directly improved the passenger experience. Inside, Boeing introduced mood lighting with larger windows and a redesigned upper deck for more premium seating options. By sticking with 4 engines, Boeing ensured redundancy and long-range reliability, crucial for airlines flying intercontinental routes. The 747-8 showed how incremental engineering improvements could keep a 1960s design competitive in the 21st century. The A380 is the undisputed giant of passenger aviation. With 2 full decks, it can carry over 850 people in an all-economy layout, but building it required some of the most complex engineering in aviation history. The wings alone stretch nearly 80 meters larger than many regional runways. Each was manufactured in climate-controlled factories in the UK, where automated laser-guided drills installed thousands of titanium fasteners. Carbon fiber composites were layered into the wing box to save weight, while high-strength aluminum alloys provided rigidity where loads were greatest. To handle the stress of long flights, engineers integrated an intelligent fuel system across the wings. Pumps automatically transferred fuel between tanks to balance the aircraft mid-flight, keeping it stable despite its massive size. Inside the fuselage, modular wiring looms were pre-assembled on the ground, then plugged into place during final assembly. This simplified what would otherwise be a tangled mess of over 500 kilometers of cabling. The high-mounted wings and engines pushed farther from the cabin reduced vibration and noise, creating the quietest cabin of any large jet. Airlines took advantage of this by fitting lounges, bars, and even showers. Though production ended in 2021, the A380 remains a symbol of pushing engineering to its limits in the service of passenger comfort. So, what do these aircrafts tell us? Every generation of passenger jet has tried to stretch the idea of how many people a single aircraft can carry. Some became icons, others faded into history. But here's the question. Have we already seen the peak of the passenger super jumbo, or will the future bring something even larger than the A380? Imagine a jet so fast it could cross the United States in under 30 minutes. We're talking about the NASA X-43. At nearly 10 times the speed of sound, it broke records and redefined what an aircraft engine could be. To understand how it reached Mach 9.6, we need to look at the heart of this machine and the unconventional way it got there. Hypersonic flight starts at Mach 5. Above that, air behaves differently because compression, heating, and shock waves become extreme. Engineers at NASA knew no conventional turbojet or rocket engine could handle sustained flight at these speeds. The answer was the scramjet, short for supersonic combustion ramjet. Unlike normal jet engines, a scramjet has no moving parts. It uses the aircraft's own forward motion to compress incoming air before combustion. At hypersonic speeds, this means oxygen for burning fuel comes directly from the atmosphere, so there's no need to carry heavy oxidizers like a rocket does. But there was a catch. A scramjet can't operate from a standstill. It only works when you're already moving several times the speed of sound. That's why the X-43 wasn't just about building an engine. It was about designing an entire flight system that could get the engine into its operating range without tearing the aircraft apart. To give the scramjet a running start, NASA used a 3-stage approach. First, a modified B-52 Stratofortress carried the X-43, attached to a Pegasus rocket booster, to an altitude of about 40,000 feet. Once in position, the B-52 released the Pegasus booster, which ignited and accelerated the combined assembly to around Mach 4 to 5. Only then could the X-43 separate and light its scramjet. This system was about speed and survival. Starting the scramjet in the lower atmosphere would have meant catastrophic heat and pressure loads before the craft was ready. By piggybacking on the B-52 and Pegasus, engineers could stage the flight in a safer, controlled environment, which was a concept borrowed from spaceplane programs but refined for hypersonic research. Here's something to think about. Why couldn't NASA just build a scramjet that works from takeoff like a normal jet engine? Drop your thoughts in the comments and we'll reveal the answer at the end. The X-43's scramjet was deceptively simple on the outside, but a masterpiece of aerothermodynamics inside. Air entered through an inlet shaped to use shock waves to slow and compress it. But here's the trick. In a scramjet, the air stays supersonic even during combustion. This was the breakthrough that allowed the X-43 to go far beyond traditional ramjets, which slow air to subsonic speeds inside the combustion chamber. The core was essentially a flow-through duct, inlet, combustor, nozzle. Hydrogen fuel was injected and mixed with the compressed supersonic air, igniting almost instantly. There was no time for mechanical compression. Everything depended on precision shaping of the engine's geometry and the physics of supersonic flow. At Mach 7 to 10, even small irregularities in airflow could cause a violent loss of combustion stability. That meant every millimeter of the inlet and combustor had to be tested and refined. Which raises the question, how do you keep fuel burning steadily in air rushing through at over 7,000 kilometers per hour? The answer lay in fuel choice and injection design. NASA used gaseous hydrogen, which is capable of igniting in milliseconds. It was injected into the supersonic airstream through carefully angled ports, creating rapid mixing. But here's the counterintuitive part. Engineers actually had to slow the air down slightly within the combustor to give the fuel time to mix and burn without letting it drop below supersonic speeds. Too slow and the engine would choke, too fast and the fuel would exit unburned. The scramjet's flame holders acted like miniature anchors for the combustion process. They kept the flame attached even as the air screamed past. This delicate balance of speed and fuel flow was the reason the X-43's engine could generate thrust in conditions that would destroy a conventional jet turbine in seconds. But as speed increased, another enemy emerged: heat. At Mach 9.6, the X-43's airframe and engine endured temperatures above 2,000 degrees Fahrenheit. No pilot could survive such heat, so the craft was unmanned. For the scramjet, extreme heat threatened both structure and airflow stability. The answer lay in thermal-resistant materials and passive cooling. Carbon composites and high-temperature alloys protected critical zones, while hydrogen fuel was routed along engine walls before injection, cooling the structure and preheating the fuel for efficient combustion. Heat management was vital. In hypersonic flight, sudden spikes could warp materials and disrupt airflow. Every engine component had to withstand re-entry-like conditions while maintaining peak performance. But even with cooling solved, controlling the craft when the engine was producing such immense thrust was another problem. At hypersonic speeds, even tiny control surface movements can drastically alter flight path. The X-43's digital control system linked flight controls with the scramjet's fuel and inlet settings. Sensors tracked speed, pressure, and temperature hundreds of times per second, feeding algorithms that adjusted fuel flow and airflow instantly. The inlet's design included components that reacted to changing conditions to keep supersonic airflow stable. Engine and controls worked as one, preventing airflow disruptions, or unstarts, from turbulence or pilot input. This precise coordination was essential before NASA could test the X-43 in the extreme environment needed to prove its record-breaking capabilities. But before trusting the X-43 to break records, NASA had to test these systems in one of the harshest environments possible. Ground testing for a Mach 10 engine isn't straightforward. Wind tunnels capable of those speeds are expensive and run for only seconds at a time. NASA relied on both physical testing at facilities like Langley and Glenn and computational fluid dynamics simulations to refine the design. In 2004, the X-43A made history. Released from its Pegasus booster at Mach 7, it accelerated under scramjet power to Mach 9.6, around 11,850 kilometers per hour over the Pacific. The burn lasted only about 10 seconds before the craft glided into the ocean, but it was enough to prove the concept. That flight didn't just set a record, it demonstrated that an air-breathing engine could function at speeds approaching orbital velocity. It also highlighted the enormous technical challenges of sustaining hypersonic flight, from thermal protection to flight control integration. And while the flights were short, the fuel system's role was no less critical. For the X-43's scramjet, hydrogen fuel had to be delivered with split-second precision. Too much in combustion could cause destructive pressure spikes. Too little and thrust would collapse. The fuel system doubled as part of the cooling architecture. It circulated fuel along engine walls before injection. This dual role required ultra-precise pumps and regulators, all designed to operate flawlessly in a high-vibration, high-temperature environment. Because hydrogen is stored at extremely low temperatures, it also served as a thermal buffer against the heat generated during the flight sequence. Every part of the fuel system was tuned to match the engine's combustion profile, making it as much a part of the engine as the combustor itself. With fuel, airflow, and heat under control, the X-43 was ready to write its name in aerospace history, even if its operational life was brief. The NASA X-43 program proved that scramjets could work, and its data is still shaping hypersonic research today. Military and civilian programs exploring high-speed transport, spaceplane concepts, and long-range missiles have all drawn from the X-43's breakthroughs in inlet design, thermal protection, and fuel-air mixing. Its record of Mach 9.6 for an air-breathing engine still stands. While the craft itself won't be replicated, the knowledge gained forms the foundation for future hypersonic vehicles. One day, flights between continents in under an hour may be possible thanks to lessons learned from this small, unmanned wedge of carbon and alloy that flew faster than any jet in history. So why couldn't NASA just build a scramjet that works from takeoff? The truth is, scramjets only operate efficiently when air is already moving through them at several times the speed of sound. At low speeds, they can't compress the air enough for combustion, so they need a booster to get them into their operating range.